Good morning. Today we're going to talk about exponential function. What is an exponential function? A function of the form fx equal to b to the power x is called an exponential function. There are some restrictions. For example, b, which is also called the base of the function, cannot be 0. It cannot be 1. And it has to be strictly positive. So no negative number, no 0, no 1 for the base. X, which is the power, is going to be called the exponent of the function. Hence the name exponential functions. The study of exponential function is pretty important for our class because a lot of the application problems when you are talking about growth, say it's a bacterial growth, or decay, say it's a radioactive decay, population growth, these are all controlled by exponential functions. We will study exponential function both graphically and exponentially and using diagrams. So we'll start with the algebraic and the graphical approach of exponential function. Let's first talk about exponential functions graphically. There are two possibilities for the graph of an exponential function. If the base is greater than 1, then the graph of the exponential function always maintain the similar pattern of the one that we're going to draw now. The left-hand side of the exponential function becomes closer and closer to the x-axis. So we say that it has horizontal asymptote at y equal to 0. Doesn't matter how much is the base, the graph always crosses the y-axis at the point 0, 1 and never crosses or touches the x-axis. So let's sum up all these properties for the exponential function. My function is y equal to b to the power x, and I'm thinking about the graph of the exponential function when the base b is greater than 1. The other situation, when the base is between 0 and 1, remember it cannot be 0 or cannot be 1, then the general graph will look like a reflection of the original graph of exponential function along the y-axis. So remember, reflection doesn't change the point 0, 1. So it is still the same. And this time, as I said, the base of the exponential function is between 0 and 1. When I said sum up all the information, I'm going to write down a couple of characteristics of these functions. So see, in either situation, the domain of the exponential function is all of real number line. So it is negative infinity to positive infinity. Whereas the range of the exponential functions is never going to be negative or 0. As I'm not touching the x-axis, the range of exponential function is always strictly positive. So it's between 0 and infinity. In my exponential function, in either side, there is one y-intercept. So I will say the y-intercept is fixed. Doesn't matter how much is the base, it is 0, 1. And there is no x-intercept because the graph is not touching or crossing x-axis. And it is true for both types of exponential function. We have talked about asymptote. Since the graph is getting closer and closer to the x-axis, I will say the horizontal asymptote in either situation is the x-axis or the line y equal to 0. And I will say there is no vertical asymptote for exponential functions. Long run behavior, we can say that as x goes to positive infinity, if b is greater than 1, y goes to positive infinity. Let's verify that. As x is going to positive infinity, so I'm growing without any bound, the graph when b is greater than 1 is also going to positive infinity. But when x is going to negative infinity on the left hand side, the graph is getting closer and closer to the height to 0. So we're going to write it down. And as x goes to negative infinity, if b is greater than 1, y goes to 0. Whereas this pattern changes as x goes to positive infinity. If b is between 0 and 1, then as you can see from the graph, y will approach 0. So my x is going to infinity and my y is approaching the x-axis, so the height 0. Whereas as x is approaching negative infinity, the y is growing without any bound, so y is going to positive infinity. So we're going to go say, as x goes to infinity, if y is between 0 and 1, y goes to 0. If b is between 0 and 1, then y goes to 0. As x goes to negative infinity, if b is between 0 and 1, then y goes to positive infinity. So these are some of the basic natures and properties of exponential function. What I want you to do, you will solve problems for exponential function, but never forget this basic setup. Our next topic will be logarithmic function, and we're going to use this basic setup to understand the inverse of exponential function, which we're going to call logarithmic function. So let's start talking about some of the problems that we have. So the following are some examples of exponential functions. So see, the first one, the base is 2. The second one, the base is 10. The third one, the base is 3. The fourth one, the base is 1/2. Each of them are non-zero, non-1, non-negative bases. So these are exponential functions. Whereas, if you think of fx equal to x squared, the base is variable, not a constant, so not exponential function. 1 to the power x base is 1, so cannot be exponential. Base cannot be negative, so negative 1 to the power x is not exponential. Even x to the power x, as the base is not constant, is not exponential function. Rounding is one other very important thing, especially for application problem in exponential and logarithmic functions. The first problem is asking you to find 2 to the power 3.4. So you go to your calculator and try to understand the value of 2 to the power 3.4, and then finally you round your answer to 4 decimal places. I would like this opportunity to remind you, if you see a problem where the problem doesn't specifically say how many decimal places you have to round your answer, you always round to 3 decimal places. So let's do 2 to the power 3.4. And I round to 4 decimal places as the question is asking. So I look at the 5th decimal place, which is 6. That's greater than 5. So I add 1 and I get 10.5561 as the answer to my question. E is a special base. What is E? E is an irrational number which lies between 2 and 3, and no one knows the exact value of E. But this special base is actually going to be extremely important for us. And your calculator has the capacity to find any power for the base E. So we're going to do that. This time the power is negative 0.95. So again, I go to my calculator. I say E, and then I raise it to the power. If you remember the problem, the power was negative 0.95. So in the power, I'm going to go ahead and say negative 0.95. I hit equal, answers the question for me. I'm rounding it to 4 decimal places. The 5th decimal place is 4, so I just erase all of the digits starting at 4 and on its right. So my answer is 0.3867. Then the rest of the information on this page are the information that we have already talked about in the first slide. So I will skip this and keep working on problems. So this problem is asking you to understand the graph of the exponential function with the base 4 for inputting values. So see, when x is -2, you get 4 to the power -2. Don't forget, there is 1 over 4 squared, which is 1 over 16. If x is equal to -1, I get 4 to the power -1, which is 1 over 4 to the power 1, and that's 1 over 4. When I get 4 to the power 0 for x equal to 0, the answer is 1. 4 to the power 1 is simply 4, and 4 squared is going to be 16. So these are the different x and y tabulation for the function f(x) equal to 4 to the power x. We're going to identify the proper graph. And as you can see, there is only one right graph. And you can check it. At -2, I am pretty close to 0 as my answer is 1 over 16. At -1, I am also pretty close to 1. It's 1/4. At 0, I am 1. At 1, I am 4. And at 2, I am 16. So that is the proper choice for the graph of f(x) equal to 4 to the power x. But we can always employ the basic nature of the exponential functions graph, which we have discussed in the slide 1, along with the vertical and horizontal translations in order to understand bunch of information about exponential functions. For example, it says use the transformation for the graph f(x) equal to 2 to the power x. So the basic graph of f(x) equal to 2 to the power x is given. Identify the graph of gx equal to 2 to the power x plus 2. Remember, this one tells you to shift the graph 2 units to the left. So I look at my original graph and shift it 2 units to the left. As you can understand, my answer is going to be the last one. And then it is asking you to talk about the domain. Remember, domain is on the x-axis, and if I look at my last graph, then the domain actually did not change much. It is still -infinity to infinity. Whereas, if you look at the range is also not changed in this problem. It's still 0 to infinity. And the asymptote, I will say that. Remember, exponential function doesn't have vertical asymptote. The only thing it has is the horizontal asymptote. And the horizontal asymptote, again, it did not change. So the horizontal asymptote is still at y equal to 0. One other way of understanding these things, I changed my x coordinate and I shifted it 2 units to the left. So what you have done for the original exponential function, if I think of these three information, you will find out domain is -infinity to infinity, range is 0 to infinity, and y or horizontal asymptote is y equal to 0. So when I'm working on my problem with transformation, I can think about the original domain versus the transformation domain. And just algebraically manipulate everything. I would like to do that all the time. So say domain, think about the original domain. It was -infinity to infinity. What you have done, you have shifted everything 2 units to the left. So your x is now going to be subtracted by 2. But remember, if you subtract anything from infinity, it doesn't change anything. So it still remains -infinity to infinity. You did not change anything in y because the changes are horizontal changes. So range was 0 to infinity. There is no change in y, so it is still 0 to infinity. And asymptote, again, this is in terms of y. The asymptote is horizontal at y equal to 0. I did not change anything for y, so it remains y equal to 0. So either I can answer this question from the graph or just answer this question from the basic information about exponential function and understanding the shift. Let's do a couple more. Our next example is, of course, for 4 to the power x, and I'm trying to do the exact same work First, I will identify the graph, then I'm going to talk about the domain, range, and asymptote. What I will do, for fun, I'm just going to write down the original versus the changed one for this question. And so to say, I'm not going to even use the graph to answer this question. So we're going to talk about the domain, the range, and the asymptote. So let's write down the original ones first. The original domain is negative infinity to infinity. The original range is 0 to infinity. And the original asymptote is y equal to 0. Let's see what type of changes we are talking about. Again, plus 3 means shift 3 units to the left. So you subtract 3. Remember, your x was 0. You shifted 3 units to the left. So you are subtracting 3. And this plus 1 means shift 1 unit up. So there is a change in x, which is minus 3, and there is a change in y, which is adding 1. Domain is change in x. So I will do minus infinity minus 3 and infinity minus 3. Again, subtracting from infinity will not change anything, so it's still negative infinity to infinity. Whereas for range, you're going to think about the change in y. You added 1. So 0 will become 0 plus 1. Infinity will become infinity plus 1. Again, adding anything to infinity doesn't change, but adding 1 to 0 changes it to 1. So that will be the range. Similarly, you can think of the asymptote. It is going to be y equal to 0 plus 1. So y equal to 1. Now let's think about the graph. This is the original graph. You're going to shift it 3 units to the left, 1 unit upwards. And as I can see now, it is going to be the graph B, which is shifted 3 units to the left and 1 unit up. And now we can answer all the questions. Think about the asymptote. The asymptote is at the line y equal to 1. The range is going to be 0 to infinity because it is not going, it is going to be 1 to infinity as the graph is not crossing the line y equal to 1. So 1 to infinity, open, and the domain is everything because you can extend your graph all along the x-axis. We're thinking about the graph of the function y equal to negative 2 to the power negative x. Again, think about this. You have two transformation. This negative means you are changing positive x to negative x. So that's a reflection along the y-axis. Whereas this is a change in y. So you are changing positive y to negative y. So this is a reflection along the x-axis. So I have both reflection in this problem. Should have said reflection along the x-axis. Think about the graph of 2 to the power x to start with, because 2 is the base. So this is the graph of 2 to the power x. First, I want to reflect it along the y-axis to get the graph of 2 to the power negative x. So that should be my picture. This is 2 to the power negative x. I said negative 1x, but if it is confusing, then you can just say 2 to the power negative x. And then you reflect this graph along the x-axis. So you get a picture like this. This is negative 2 to the power negative x. And see, I'm going to do the domain game one more time. So again, if you just forget about the graph that we have drawn, think about the original domain versus the change domain. And think about the changes. Domain is along x-axis and the original domain is negative infinity to infinity. What change you have done to your x coordinate? Well, you multiplied negative. So multiply negative with negative infinity, you get negative of negative infinity. And multiply negative with positive infinity, you get negative infinity. So this is still infinity and negative infinity, we just write the interval from the smaller to the larger. So we'll go ahead and write it as negative infinity to infinity. So see, there is no change in the domain of your final function. It's still negative infinity to infinity. Range. Range is change in y, and the original range is 0 to infinity. And what you will do, you will now multiply negative, because that's the change in y, to your range numbers. So you will get negative 0 and negative infinity. Negative 0 is just 0. And again, you write interval from smaller to larger. So I'm going to go ahead and say that this is negative infinity to 0. Now look at the final graph. See the range of your final graph. It is going all the way to negative infinity. And the highest point on the graph is at 0. So the range is negative infinity to 0. Makes sense? Asymptote. The asymptote for the original exponential function is y equal to 0. The change I have done is multiply negative to the y coordinate. So I get y equal to negative 0, which is y equal to 0. And see your green graph, the graph is closer to the x-axis. So the height, y equal to 0. So there is no change in the y-intercept. The y asymptote. So finally, we're going to pick the right graph. You know the green one is the right graph. That makes your life so much easier. We're going to say the third one in this list is the right graph for the function y equal to negative 2 to the power negative x. The next question is asking, use transformation to find the domain, range, and asymptote for e to the power x minus 3. Now, as I have said, e is a number between 2 and 3. So e is at least greater than 1. So the graph of e to the power x, if you think of it, it's going to be the graph of this form. That's y equal to e to the power x. But now I have a transformation. And this transformation means I'm going to shift the graph. It is a change in y. So shift up by, shift down by 3 units. So let's talk about the domain, range, and asymptotes first. It's the original versus the changed one. So the original domain is on x-axis, negative infinity to infinity. Now there is no change in y, so it will still remain negative infinity to infinity. The range is y-axis, and the range was 0 to infinity, but now I have shifted it down by 3 units, so subtract 3. So you get 0 minus 3, comma infinity minus 3. Just remember, if you subtract anything from infinity, it doesn't change anything. So I get negative 3 to infinity as the range. And finally, we talk about the asymptote. Well, asymptote is also represented by y. It is y equal to 0 originally. Now you subtract 3 from it, so you get y equal to negative 3 as the horizontal asymptote. How about the graph? All I need to understand is what is a shift of this graph 3 units downwards. So 1, 2, 3. Whatever we were expecting at 0 will now happen at y equal to negative 3. So that will be the basic graph for the function y equal to e to the power x minus 3. And I will pick the right graph. And as you can imagine, the right graph is going to be B. The last article of exponential functions for our class today is talking about some of the application problems. We'll do a bunch more application for exponential function afterwards, but today we're going to talk about application for exponential functions that involves compound interest. The compound interest formula is A, which stands for the accumulated balance, or we often call it the final balance. P is the invested principal. is the rate of interest in decimal. So change it in decimal number. N is number of compoundification. It's how many times you are getting interest per year. And T is time in years. So that's the compound interest formula. For our exams, I will provide you with this formula so you don't have to remember this. The second formula is called the continuous compoundification formula. Again, I will give you this formula, and this one tells you if P is your investment, the final amount accumulated is A, and the rate of interest is R for T years. For continuously getting interest, the formula will be used is A equal to P times ERT. Let's do examples and it will make better sense. Find the accumulated value of an investment for $10,000 for 5 years at a rate of interest of 5.5% if the money is compounded quarterly versus continuously. So what is compounded quarterly? That means per year you are getting 4 times interest. So N is 4. What is the principal invested? It's $10,000. So P is 10,000. Time you have invested for 5 years, and the rate of interest is given to be 5.5%, which I'm going to change to decimal, and it will be 0.055. Always remember, in our problem, never use percentage, always use the decimal expansion of the percentage. And these are the information for both sides of the problem. We're just going to use the formula. So final amount accumulated, A will be 10,000 times, this is the principal, times 1 plus rate of interest, which is 0.055, over the number of compoundification. For you it is 4, to the power N times T. N is 4 and time is 5 years. So this is the expression that we're going to simplify. And when I ask you to find the amount accumulated continuous compoundification, so this is continuously, every nanosecond you are getting an interest, how much is the money accumulated? So that is the principal invested, $10,000, times E to the power rate of interest 0.055 times 5 years. So let's find out both numbers in our calculator. Because it is a money problem, we're going to round our answers to 2 decimal places or to the nearest cents. So for the first one, I am going to divide 0.055, that's the rate of interest, by the number of compoundification, add 1, and I'm going to raise this number to the power 20. Remember, it was to the power 4 times 5, which is 20. And then finally, I multiply this answer by 10,000. Round it to 2 decimal places. Because the third decimal place is 5, I add 1 to the previous decimal place. So it becomes $13,140.67. Now we will see how much money will be accumulated for the same time, but if we went for continuous compoundification. So we are going to first calculate R times T. R is 0.055 times T is 5 years, and then put it in the power of E. So now I will say E to the power 0.275 and multiply this number by 10,000 and round it to 2 decimal places. Again, the third decimal place is 6 more than 5, so add 1 to the previous decimal place. Your answer will be $13,165.31. So even if I invest the same amount of money, money with the same rate of interest, with the only change is one time the money is being compounded at 4 times per year, and the other time it is compounded continuously. I see that the amount that will turn out as a final amount is bigger in the continuous compoundification situation. But it is not always true. It depends on the rate of interest as well. For example, now I want to invest $12,000 and I want to invest it for 3 years, with the only exception is now I want to have 7% interest rate and the money is going to be compounded monthly. Monthly means it is compounded for 12 times in a year. So our rate of interest in the first situation is 0.07 because it's 7%. Time is 3 years. Principal invested is 12,000. So let's find out how much money I'm going to see after 3 years. So that will be principal invested times 1 plus rate of interest divided by number of compoundification to the power number of compoundification times the number of years. Whereas when I'm doing continuous compoundification, the rate of interest is 0.0685 because it is 6.85%, a little less than the continuous than the monthly compoundification. So money accumulated in this situation, because time is still 3 and the principal is still 12,000, the money accumulated after 3 years will be 12,000 times e to the power 0.0685 times 3. And we will find both of these numbers and round to the nearest cent or 2 decimal places. So for the first one, I'm going to first divide 0.0686 because that is the rate of interest. Oh, this time I'm doing the compoundification monthly, so let's change those numbers in the calculator because the rate of interest is 0.07. So 0.07 divide by number of compoundification, add 1, and then you raise it to the power 36. How come raise it to the power 36? Remember 12 times 3 is going to give you 36. So I will hit equal and then multiply by the principal invested, which is 12,000. Round it to 2 decimal places. Third decimal place being 7. I add 1 to the previous decimal place. I get $14,795.11. And we will now find how much money we will get if we have compounded the money continuous interests. So this time your rate of interest is 0.0685. So first you do 0.0685 and multiply that number by the time, which is 3 years. And then you raise e to the power 0.2055 and multiply that number by the principal invested, $12,000. And I get $14,737.67. And as I have said, since I am compounding continuously, our investigative ideas would tell us I must get better turnout. But as I have seen in this problem, because the interest rate is lower, even with the compound interest continuously, I earn less money than I earn in compoundification only 12 times a year versus continuously. And my interest rate is higher. So higher interest rate, it doesn't matter what type of compoundification I'm using, has the chance of earning you more money for investment. The last problem is a problem which is a little intricate. So this problem has given you the functional values for an exponential function, and we want to find out the parameter d. Answer in terms of parameter d. So find a formula of an exponential function satisfying f of 1 equal to 3 and f of 3 equal to d. So what I will say, because I do not know the exponential function, I will go ahead and say that let's let fx equal to a times b to the power x and see how I solve this. F of 1, you know, that is 3. So 3 equal to f of 1 equal to, look at this, a times b to the power 1. So what I get? I get a times b is equal to 3. So b is equal to 3 over a. There is one other information, and that is d equal to f of 3. But what is f of 3? If I put 3 in the original expression, I get a times b cubed. But remember, we just seen b equal to 3 over a. So I will say a times 3 over a whole to the power 3 is equal to a times 3 to the power 3 over a to the power 3, which is equal to 3 to the power 3 is 27, and a over a to the power 3 is a square. And don't forget that is equal to d. So what does that tell me? It tells me d equal to 27 over a square. Multiply a square on both sides. So I get a square times d equal to 27, implies a square equal to 27 over d. Then I take the square roots on both sides. If I do so, I will get absolute value of a. Remember, I'm taking square roots, so I will get absolute value. Don't worry about the right hand side. It's just going to be square root of 27 over d. Remember, I get two answers. A equal to square root of 27 over d, or a equal to minus square root of 27 over d. Which one I pick as my right answer? Well, remember, what is b? b is 3 over a. And b is the base. That means b must be greater than 0. So, if a is less than 0, then b is less than 0, means, and it cannot happen because b is the base and it must be greater than 0. So it means your a must be greater than 0. So that tells me the answer to the question. Because now I know definitely a must be the positive value, square root of 27 over d. And I will say, so the exponential function that you were trying to find out is given by remember the form. The form was a times b to the power x. That's how I started the problem. And I know a, my a is equal to square root of 27 over d times b. b is 3 over a. So 3 over square root of 27 over d, that's your b, whole to the power x. And that answers my question. So we're going to stop here. And as usual, if you have any further question, please email me and I will get back to you as soon as I can. Please keep working on these lecture notes so that when we come back on our class for logarithmic function, you are going to start with a bunch of information from the exponential function. Will be helpful for us to understand logarithmic function. Goodbye.